So welcome back. We have a midterm on Tuesday, so that's October 8th. October 8th? That is October 8th, right? Yeah, it's October 8th. Okay. And today we'll spend, I said we're gonna do the, after, anyways, the point is I'll go over the midterm review first because just in case we run out of time the other way around. So we start with midterm review, and then if we finish it early, which I think we probably should, then we'll continue with where we left off in the last class. Okay. Cool. So I sent an announcement on eClass, which I guess you should have all seen and got an email about, with all the details that I could think of about the midterm. Yeah, okay. And so for studying, so anyways, point is review that for like specific details about the midterm. Studying, here's the best tips I have, which is that review the assignments. The questions are going to be, they're multiple choice, as I said, very similar to the assignment questions. Select all that apply. If you can do the assignments, you can almost surely do well in the midterm. There's some extra exercises in the course notes and examples, especially like in the probability section, there's some like extra exercises in there. Those are helpful to do. And then there's the formula sheet. So I recommend understanding everything on the formula sheet and how to use it. I tried to more or less put only the things that are sort of required on the formula sheet. And just a note, I added like one line about integration to the formula sheet yesterday, which is just like the integral of x to the a. That's the only integral you're going to need to know. Okay. And I went through the midterm and I looked to see that there was no formulas on the midterm that you would need that are not on the formula sheet. So I think it should all be covered. And in terms of like loss functions and stuff, those are mentioned within the question if you need to use them. Okay. So today we do this like midterm review. And what I decided to do is kind of, I went through all the different parts we covered and then like mentioned the most sort of important parts, because obviously when I taught it, there was all sorts of details, and then it turns out some of the details maybe aren't so useful as others. So I kind of mentioned the most useful details, and then I went through the midterm and double checked that everything in the midterm was actually covered in this review. So I think that's true. So if you understand all the stuff here, then you should be good for the midterm. But then again, all the stuff here is kind of everything we covered maybe. So I don't know. We'll see what happens. Okay. And someone said, I understand the concepts will be the same, but will the midterm be of the same difficulty or harder? And it definitely won't be harder. And there will be no, like, there shouldn't be any like long calculation questions. There was some like derivatives that took a bit of time on the assignments, or some probability questions that required like quite a lot of addition or like math steps. There shouldn't be too many math steps in any of the questions. But yeah, otherwise it's like very similar style and stuff. I just tried to remove all the like longer math style questions because you don't have that much time. Okay, so yeah, we review section by section. So we start with math review, and there was a few things we covered in the math review, and here are the main things. There's like, clearly it's important to know about the sets and the notation. Like sets keep getting used later on for describing event spaces and outcome spaces and functions and what they map to and everything. So like you'd be doing a disservice not to understand what a set is, because it just keeps getting used over and over again. So anyways, yeah, we write sets with these like, that's right. We write them with these curly brackets. And things like the natural numbers and the reals are also sets. And then there's a bunch of operations we can do on these sets. Okay. And a pretty important thing that keeps coming up is this set builder notation. And we use it to describe sets. And the way, once again, that it's read is you start with like the object on the left. So here it's like this variable x, it's going to be a natural number. And this is the such that condition. So this like bar means such that this kind of condition holds. So for instance, on the right, you get the set like 0, 1, 2. And as you have seen, it becomes important when we start talking about like sets of functions and specific types of functions. Like in the last class, we talked about these linear functions. And so then we start, like this notation becomes quite important. We say like, oh, here's a function. It has this type of form. And then we could have added other conditions here saying like, and it has this type of, like it looks like a linear function, or maybe it's a polynomial function and so on. So these are important. Okay, and the way we usually create sets of tuples, and tuples become important for multiple things, like for the multivariate random variables and stuff, is we use this Cartesian product, okay? So a Cartesian product creates a set of tuples, not sets. Yeah, Cartesian products create a set of tuples. Okay, so a Cartesian product is always a set. Inside the Cartesian product, you have tuples. And this is like the definition of it. So, okay, then there's these things called vectors, and the main operation we're going to do with these vectors, at least for the midterm, is just like these dot products. So you just need to remember what this notation means. I guess this isn't in the formula sheet, but I expect you to know that this transpose thing means it's a dot product, and you can write it this way, and you just multiply each of the corresponding indices, and then add all that together. Okay. Cool. And then there's functions, and yeah, this is pretty useful to know the notation here because there can be some confusions that I've seen. Okay, so we write this to mean this is like this is any function, right, that maps objects from this set to this set. In this case, the set is real numbers to real numbers. An example of a specific function that satisfies this is the function f of x equals x squared. Here, because of the fact that I've defined the function in this way, you know that x has to be a real number, and that the thing it outputs itself also is an element of the real numbers. And of course, if you take a real number and you square it, you get a real number. Okay. Similarly, you can have a function that now doesn't just map real numbers, but it takes two-dimensional real numbers. You can think of these as vectors. And so I write it like this, and here's a specific instance of this function. Okay, so it takes in this vector. You can explicitly write down that there's two indices or dimensions of the vector. And then you define a function which just uses those two indices. And so here you can see it takes x1, it adds it to 3x2 squared, and this thing is a real number, which makes sense because this function better outputs something that's a real number. Okay, so this is pretty straightforward, I hope, but it gives the intuition to what's going on with this learner function. And so in this learner function, okay, this thing called the domain, it's a more complicated set, fine, but it's still a set, just like R2 was. It outputs things, okay, it's not a real number, but it's another set. It's a set of functions. So you know that this function is going to take in something that is like this data set of n objects, and it's going to output something in the codomain, and those are functions. Okay, so an example is, for instance, you might have the following data set here. I've assumed that n is equal to 2. Okay, this thing, I can write, it's an element of that thing above, right? And then so since it's an element of that, I can pass it as input to the function. And then I need to output something that is in the codomain. And here I output the function f, where f is just the following function. And this function, once again, is, x here has to be a real number, because that's what this definition says here. And this output here is also a real number. It just adds things together and multiplies things. Okay. That is how you read these things, and there's all sorts of in-betweens of what the functions could take as inputs and stuff. But really, the thing to remember is this thing is a set. The domain is a set. The codomain is a set. Functions take as inputs elements of this set. They output elements of this set. That's the formal thing to remember. Okay. Yeah, and I'm emphasizing this because obviously everything downstream later on assumes that you know this notation. So it's important that you understand it quite well. Okay, summation and integration. Also, once again, it's going to be very useful in probability, so we should know it. And so summation, if you have, for instance, a tuple here, right, x1, x2, x3, then you can write the sum over the elements in the tuple in two different ways. You can write that, okay, we use this summation symbol. You sum over all the elements in this calligraphic x, or you could write that you just sum its the elements by their indices. These are equivalent notations, as you've seen. And this just means this. Okay, just this is a shorthand to write the sum. And as we've seen, this is useful notation to have because sums can get very long and they can be complicated objects, and you don't want to just write all of them on your page. And then you can do the same thing for functions. And we saw this with the loss functions and other things in this class. And yeah, you just put the function in here and you say, okay, I'm summing over all of the elements in some set, or I can say I'm taking the sum over the specific elements by talking about their indices. Okay, this is the definition. Okay, then there's integration, which is like the kind of version of summation for continuous sets. Okay, here we had a discrete set of elements, and then we took the sum of it. If you instead have another, like a set y, which is an interval like this, then you would talk, if you want to like, there's this idea of accumulating all of its elements or the function of all its elements, then you use an integral. Okay, and the integral notation is the following. You write like the thing you're integrating over, which is the set y here. And then you write the thing you're integrating over, or sorry, the thing you're integrating, which is this function. And then you write this little dy thing to point out that you're integrating. It's the integration notation. Okay, you don't add this dy for summation. Yeah, and so you like if it's an interval, the notation we use is like you put a at the bottom, which is the start of the interval, b at the top, the end of the interval. You take the integral, and if the function is something like y to the c, and so this is the only integral you're going to need to know for like all in all, like these yeah, I guess like your function variable raised to some power c. Well, then the integral of that is just the antiderivative is what it's called. It's like y to the c plus 1 over c plus 1. So this is on your formula sheet. This is the only integral rule you need to remember. And then you plug in b, you plug in a, and take their difference. I guess I didn't write that, but it's on the formula sheet. Okay. And okay, so then maybe a useful thing that comes up is when sometimes we want to integrate and sum over like different variables, and then you get a mixture of like summation and integration, and you can get like mixture of multiple summations, mixture of multiple integrations. You've seen this before. But here I do an example where you integrate and you sum in the same thing. And I just wanted to like explicitly mention what this kind of means one more time, because it keeps coming up, right? When we have these like features and labels, you're integrating maybe over the features, then you might be integrating over the labels. If it's regression, you might be summing over the labels. If it's classification, and so this becomes a very important like thing to understand what's actually going on. Okay, so this happens when we have these multivariate functions. So here I'm passing in x and y, and I've just defined an explicit function, x times y. And then you have like two sets that you might be interested in. X here is discrete, has a finite number of things, and y is this continuous set. So we're going to integrate over y, and we're going to sum over x. So what I might be interested in is like the following equation. This comes up in the probability world. And here I'm going to sum over this function, and then I'm going to integrate over the y variable. Okay. And the way you do this is you plug things in. So I've plugged things in this equality here. And then you evaluate. And the way you think about evaluating is you do one at a time. So like I'm going to evaluate the sum, right? And this sum is over x. So I'm just going to hold y as like a constant for now. And so I just take the sum over x. So I evaluate this. If I do that, I get the following. I just like really explicitly written out what the sum is. Since I don't have values, I just plug this in. Okay. And then after that, I do the integral. So now I'm just left with a function of y. And so I integrate this thing, and that becomes the following. Okay, so like procedure is just like expand one at a time. If this was a double integral, you'd integrate the inside, and then you'd integrate the outside. Okay, and each step kind of like removes one of the variables. Great, okay, so probably all this is hopefully everyone's aware of. And okay, a very important thing is this derivative stuff. It's pretty important for the midterm. It's going to be very important for after the midterm. And so, yeah, there's derivatives and there's partial derivatives. So if you have like a univariate function, so a function of one dimension, such as x squared, you write the derivative as like f prime or this df by dx notation. And there's all the derivatives on the formula sheet that you would need, but the derivative of like x squared is 2 to the x. That's its derivative. And then you can also sometimes, sometimes you can take the second derivative or the double derivative, and that's just the derivative of the first derivative. And so that would be like the derivative of 2x, and then you get 2. And then if you have functions over multiple variables called multivariate functions, or it could be like multiple, like a vector can represent these multiple variables, then you use partial derivatives. And so partial derivatives are written as like this, they use this like thing that they call like del or partial notation, and it looks kind of like a 2, I guess. And so anyways, this means the derivative of f with respect to x1. Okay, so there's two variables, there's x1 and x2. This is the derivative of f with respect to x1. And the way this works is you hold all the other variables constant in the function and you just take the derivative with respect to x1. So in this case, you would look at this, you're like, okay, I'm holding every other variable as like a constant, so this is just a constant. The derivative of that is 0, and so I just need to take the derivative of this, and so I get 2x1. And then the similar story for x2. Okay. That's all you need to know there. And these, like, there's common derivatives and properties of those derivatives, like the chain rule, and I also added this product rule, which I kind of, I guess, forgot at the very beginning, but there's a product rule, you should know it from calculus. It's on the formula sheet. Yeah. Okay, so that's all the math review. Is there any questions about the math review? Yeah. Sorry? There's not going to be any questions about gradient, but like you can review the gradient. Like the gradient is just put all these partial derivatives in a tuple, or like put them in a vector with comma separated. So it's not that interesting. Like if you can do this, you can get the gradient because you just need to take the partial derivative of everything. Yeah. But yeah, you don't really need to know what a gradient is for the midterm. Yeah, question up there.
I had a question about the learner function. Like you have the data set is in the form r times r to the n. So what does n represent?
So if you go here, you're talking about this thing? Yeah, so the question was like, what does n represent here? So n represents the amount of like data points you have or samples from the data set. So in this case, you would think of like, oh, you have 2 data points, and you can think of this as having like 2 feature label pairs. So that's what it represents. Usually we keep it like, we just say n as like you have n number of these feature label pairs. When you're actually going to implement things, for instance, in code and stuff, you're going to have like, let's say 10,000 data points or something like this, or yeah, you're going to have some amount, and that's what n is going to be. So here you have like you have like 2 data points, and then you can use them in some way to learn. And here I like use them in this like arbitrary way. I like subtracted 2 of them, added 2 of them. But that comes up in the machine learning part, which we haven't got to really yet. Yeah. Yeah, so for the purposes of this course, you can like always interchange them, and it doesn't really matter. Okay, probability. So this is probably the most questions are related to probability stuff on the midterm, I'd say. It's also the biggest section we covered. So yeah, okay. Here are some of the most important concepts, and then most of the formulas and stuff, I just tell you to refer to the formulation. Okay, so there is this idea of an outcome space and an event. And I've noticed that there's been some confusion about this, so I say it one more time because it's definitely important to know these differences. So you're going to be told what an outcome space is. It's just going to be like a set. Okay, so first of all, it's a set. This is the outcome space. It's a set. And it has things inside the set which are called outcomes. And these are like, when you think about an experiment in probability, it's like the possible outcomes that can happen. Like rolling a dice, you can get either 1, 2, 3, 4, 5, or 6, or whatever. And then what you really need to know is that an event is just any subset of the outcome space. And when we write out like subset, that means it could also be the entire outcome space itself. Here, this is like including the whole outcome space. Okay, so it's just some subset. That's an event. And like an example might be the subset 1, 2, 3. And then you would say like, oh, what's the probability? Okay, we're going to talk about probabilities in a second. Yeah. So this could be a subset. You just take 1, 2, 3 and put it in a set. That's an event. That's the difference. Okay. Then there's these things called probability distributions, which is what we actually care about in some sense, like about all probability. We care about calculating the probability of things. To do that, we use these probability distributions. Let me finish this first. So this is the symbol we use for a probability distribution, this like double bar P thing. And the important things to note is that this object will take as input events, and it'll always output a value between 0 and 1. Meaning the probability. The probability can't be like 2. You can't have 200% chance of something, and it can't be negative. And it's taking in these events. So that's where the events are useful. And so you would write something like this, the probability of this event, right? Where this thing is your event. Okay, I'm going to talk about the interpretation of that in 1 second, but what there's a question?
Events always have to be denoted in brackets.
Yeah, they're always sets. Like events are always sets, so they better be like, what I mean by that is like, when you write an event, so an example of an event, this thing better be written as like 1, 2, 3. It's not equal to this. Like that's not an event. Right? An event is like a set of outcomes. And well, it's a subset of the outcome space, so obviously it contains outcomes, and it's just some set of the outcomes. Sometimes you have like more complicated events, so not in, but like where your outcomes are actually tuples, and that's okay. So you might have, but not for like this dice case, anyways. So that this wouldn't work here, but anyways, yeah. So the elements inside the event can be tuples if the tuples are the outcomes, but the whole thing is a set. It's a set of outcomes. Yeah. So the events can be the set, which is the outcome space, but you wouldn't, like, an example is like, this thing can be X, but it's not, it can't be the set that contains X, because this is a set of a set. Like, so once again, the event is a subset of the outcome space, so it contains outcomes, and it's a set. This thing contains all the outcomes, and it's a set, so it's a valid event. This thing contains one thing, which is the outcome space. That is not an event. Okay, that this is not an outcome. This is the set of all outcomes, so that would not be acceptable either. Okay, so anyways, we talk about probabilities of events. And before talking about that interpretation of it, let's define these random variables. So there's things that are called random variables. These random variables are going to be useful things to talk about. Like they're used in lots of notation things, and let me just tell you what it is and then how we use it. So we write a random variable as usually a capital letter. This random variable takes values, or like it belongs to the outcome space. So it takes a value of an outcome, right? So random variable is equal to some outcome. And we say it has some distribution. So that means like the random variable is following this distribution, and you would say maybe like the random variable describes the roll of a dice. So it takes either 1, 2, 3, or whatever. And the probability of getting anything is governed by like this distribution. How do we use it? Well, we write things like this, which is that the probability distribution of this random variable being in this event, right? So we write this type of notation, and this just denotes the following, which is the probability distribution with the event as input. So this is like the formal mathematical thing. And we write this kind of notation with random variables quite often to mean the exact same thing, okay? So notice how this thing does take as input an event, and this is just like notation. I should really write that this is like the definition of it. So when we write X is an element of the event, you should really think it's just the probability distribution with the event as input. And the way you interpret this is like, if the event was 1, 2, 3, you would say the probability that randomly rolling a dice is the value 1 or 2 or 3 is whatever this function outputs. Okay. Yeah. Okay, and so before I get into how to calculate these things, I just want to mention some common notations you're going to see that I think I mentioned before a few times, but it's good to highlight because you should always remember this is like the true underlying thing you want to write. And so, yeah, here's some shorthands that end up being used a lot in probability. So common notation. So let's assume that, first of all, the case of the event containing just a single outcome, right? So it is the set of just one outcome. Maybe let me finish these and then I'll take the questions. So if the event is just a single outcome, like this is a subset of the outcome space, right? So it's just one outcome. Notice how it's not just an outcome, it's a set of one outcome. Then we might write things like this, which is the probability that the random variable equals to this outcome. This is really shorthand saying that it's the probability that the random variable belongs to this set. Okay. So don't get confused thinking, oh, now I'm taking as input outcomes. This really means this thing on the right, which is it's taking in the event, which just contains the outcome. Okay. And then two more cases, you'll see that when this thing is an interval, when the event is an interval, there's some other notation that gets used, which is, yeah, like so formally you would write this. It's the probability that the random variable is in the event. That's what you would formally write. But we use the shorthand notation of this, which is like x is less than, or sorry, greater than a, less than b. And once again, this notation means the following. And so really, I guess everywhere I should put that this is like the definition of all this stuff. Okay. Yeah, and similarly, if you have like an interval that goes to infinity or goes to negative infinity, then the formal way to write this is the following, where you actually put the event here. But there's shorthand that gets used, which is just saying like x is less than b, which means x is in the event, which is the interval of all values between negative infinity to b. Just like shorthand notation. And the reason I'm like introducing this again is because this is what you're really going to see in probability world everywhere. And so it's useful to know this. Yeah.
Like lowercase x, uppercase x, and outbound x.
Yeah. Okay, so the question was, what's the difference between, like, there's three kind of objects. There's this calligraphic thing. Okay, let me write things in. There's a calligraphic x, there's a capital X, and there's a lowercase x. And the difference is, okay, first of all, there's like difference in what we usually, like there's a difference in terms of like what we usually use these things for. But like if I give them the explicit definition that this is an outcome space, right? So this is what I'll usually use it for. These calligraphic things, and that's just a set of outcomes, right? It's just like a set of objects. We call these objects outcomes. But at the end of the day, it's just a set. Okay, so the outcome space is just a set. And then you have two other things, which is this like capital X. And if I call this capital X a random variable, then what that means is that X, first of all, belongs to some outcome space, let's say calligraphic X, and it has a distribution P, which means we can talk about like its randomness. We can talk about its the distribution, that the random variable takes something and so on. So the important thing is that it has this extra piece of information, which is the distribution. And because of that, we can talk about the probability of the random variable being something. We can talk about the expected value and so on. And then sometimes, like, we'll use these lowercase letters to just be like a variable or an instance. You can go with an instance or a fixed thing, whatever. And so this has nothing to do with like probability anymore. You should think of it as just like as a normal variable. So you would write little x is an element of some set. Nothing to do with probability, it's just like is some value in this set. And so that's how these are used. So you would never write this, with little x here. If little x is just a variable or just an instance of the random variable. You really use a random variable in here. That's the story. The capital X still takes values in the outcome space, but we can talk about the probability of it taking some set of outcomes. So we can say like the probability that this random variable belongs to this because it has some notion of probability. If I use the little thing, then there's no probability distribution attached to it. I can't talk about the probability of anything. So yeah, that's the main story. Like basically, if you have a random variable, you can talk about its probability and things. It's not an event. It's just it's going to take a value of some outcome. Yeah. Oh, the second x, the random variable. I can even put a random variable x. So we think of x as being like this random thing. We don't know what it is. The probability of it being anything is determined by this. And then, like once you like sample it or get its value, like you run the experiment, you get some actual outcome, and then we talk about that as being like this little x, that's its instance or it's the actual value it takes and stuff. Yeah. Which one? Wait, sorry, the random variable part or the probability? Oh, this thing? Oh, this? Oh, yeah. So I'm saying like you have a probability distribution. It takes as input events, which are just like subsets of this. So this is like, this is what this thing does. It takes in events and it gives you the probability of those events. Okay. And then we use this notation here. So like, notice what is this thing? This is not an event. This is like I'm writing like X element of this. Like this is just like some math notation. But when we write this, you should think of it as being exactly the same as writing this. So this is just like a notation we use to describe exactly this object on the right. And this object on the right, we have an actual definition for and everything. This is the probability distribution it takes in events, just like a normal function would. It takes in these objects which are events. This thing is just like some other symbol. But this symbol is the same, should be thought of as the same as this. And like one reason to write it like this is it's much more intuitive to like understand what's happening. This is like you should think of it as like the probability that X belongs to any, like takes on an outcome which is in this event. So once again, if this event is like 1, 2, 3, you would read this as like X belongs to, like it takes on the value of 1, 2, or 3. It's like the probability of that. So yeah, it's used as like essentially more readable notation in some sense. There's like more mathematical story behind all this, but for this course, you should just think of these as like the same objects. Yeah, so once it's in terms of like, you can define the function however you want, but then the question is like, how do you interpret what the function outputs? And the way you interpret is like when you pass in this event 1, 2, 3, you're not saying, oh, it's the probability that you get all 3 at once. You're saying it's the probability of getting any one of those outcomes in the set. Okay, so when you write something like this, you should read it as this is the probability of getting any one of the outcomes in the set. It's the probability of getting anything in that set. And so equivalent notation that we use is this. And this kind of makes it a little more explicit. It's the probability of getting an outcome. And here, like we think of it as like a random outcome. And which outcomes do you care about? The ones that are in this event. Okay. There's some questions online. When is P x equal to 0? I think I will go over that very soon. For the event with a single outcome, can you write P of just little x the same way you write this? So the answer is no. Like, you shouldn't write this. And once again, this is just like notational convention, but like you wouldn't write this ever. You wouldn't write like probability distribution of little x. You could write this though. This is actually true. This is actually the like exactly what I mean by this equality here. This thing is just equal to this, the probability of this event. Let me answer a couple more here. So, what do we mean by E equal to infinity to B notation? Yeah, so like this, what do I mean by this notation? I mean that this is the set, right? This interval is a set. And I can pick any set, and in this case, maybe the outcome space. So, okay, I haven't told you what the outcome space is, but like if I chose the outcome space to be, let's say, the real numbers, then clearly this event is a subset of the real numbers. So that all makes sense. Like E in this case is a subset of X if it's the real numbers. So like the outcome space I could have chose here is the real numbers. And the probability that small x belongs to E should be valid if it's an instance variable, which is in the outcome space. Should not be valid. Yeah, so like, I mean, once again, validity of like this kind of notation in this, so I guess I should write that like this is not good, is in terms of like how we define the conventions of like how we write notation and stuff. And the convention is like, the notation that's valid is you put a random variable here, and you say it's an element of this, of some event. You can't, this thing better be a random variable, in the sense that it has, like this distribution that's being used here has to be the one associated with X. And that's what I mean by this. So you have a random variable and it has a distribution. You can then use that distribution to talk about the probability that that random variable is like an element of some event and stuff. Yeah.
The 3 intervals that we have out there, the first one, why wouldn't it be A is less than or equal to?
Oh, yeah, it should be this. Yeah, this is like the formal thing. Usually it doesn't actually end up mattering because, well, we'll see in a second. But like let me just maybe tell you the story. It's like the way you're going to calculate this is using a PDF, because this is like a continuous interval. And the integral, if you exclude or include a single point, like if you integrate between A inclusive and B inclusive or not, it's going to be the same value. So it doesn't matter. So you can write either one for these things usually. But yeah, to be completely correct, this is how you would write it to like completely match this interval, as this one has in this. Yeah. Okay, let's keep moving for the sake of time. So, okay, so this was like, all I've done so far is I told you what an outcome space and an event is, and then I told you what a random variable and a probability distribution is. And we talk about like the probability of events, or we say the probability that the random variable is in the event. It's the same thing. Okay. What are the interesting things is like there's, okay, we're going to want to calculate these probabilities, but before we do that, it's useful, it turns out, to break these things into two cases. And those two cases are essentially dependent on what the outcome space is. So like if you have a random, okay, so there's discrete random variables and there's continuous random variables, right? These random variables belong to outcome spaces. And for the purposes of the midterm, there was like some extra details I said that like, oh, you can have continuous spaces before, but as long as they have, like there's some event in there that's countable and whatever. Anyways, forget about all those details for the midterm. Like if it's a countable outcome space, which means like it's a finite set or like it's the natural numbers, then it's a discrete random variable. So if you have a random variable x that belongs to this set here, then this is a discrete random variable. Why? Because the outcome space is countable. If it's an uncountable outcome space, then you have a continuous random variable. And right here, like the thing I didn't write is that the random variable belongs to this outcome space. And it also has like a distribution, but I'm not writing that instead. That's the difference. Okay, so now I guess the important thing for the midterm and stuff is how you calculate probabilities. And the way you calculate probabilities is you use a PMF or a PDF. And this depends on the two cases. Is the outcome space this countable or uncountable? And the way we describe this is like, is the random variable, is x discrete, or is the random variable continuous? So there's the two cases. There's two different formulas. So yeah, for the discrete case, this probability, so this is, right, we've talked about this quite a bit now. It's like, this is the probability of x being an event, which is the same as the probability of just the event, is equal to the sum of the PMF function, right? So this PMF now takes as input outcomes, not events, right? The event has inside, it's a set of outcomes. So what do? You just sum over all of the outcomes in the event of this function here. Okay, so this is how you're going to basically calculate everything. It's always like, if I ask for some probability of something, what you do is you go find the corresponding PMF or PDF. Well, I guess the first thing you do is you check, is the random variable discrete or continuous? Then once you find that out, you know if you should use a PMF or a PDF. And then you go use the corresponding PMF or PDF to calculate things. So yeah, so x is discrete, I use a PMF. PMF takes as input outcomes, not events. Okay. Events are sets of outcomes, so this all makes sense. I'm taking outcomes from the event, and the event is a set of outcomes. And then if y is continuous, it's almost the same story. Now you just have this PDF thing. It still maps from outcomes to some numbers. And the way you calculate the probability of a random variable being an event is you use an integral. And once again, the integral here is over the event, similar to how the sum is over the event. Right? And once again, events are sets of outcomes, so it all makes sense. These things are outcomes in here. Okay. This is like the thing you need to know for calculating things. And then after that, there's like all sorts of common distributions. So common P's that are used and stuff. And some examples are like this Bernoulli, this normal, Laplace, and whatever. And those are in the formula sheet. And if you want to calculate anything with them, they have corresponding like PMF and PDFs with them also in the formula sheet. So you would just use those to calculate things. So if you're told you have like a normal distribution or like a uniform distribution, then you just go in the formula sheet, find its corresponding PMF or PDF, and use that for your calculations. Okay. And then after that, this was like this was like where you just had a single random variable. Then there was the case of when you have multiple random variables, also called like multivariate probability. And here I just do the case with two variables. That's really all you need for the midterm, and throughout the course is just like this two, for the most part, case. So we just cover that. Okay. So this is the case where you have a random variable, which is now a tuple of random variables. In this case, it's a tuple of two random variables. Okay. Its outcome space is just like this Cartesian product of the outcome spaces of the individual random variables. So all these formulas are on the formula sheet, but what I wanted to mention is there's like a few different things, like probability distributions that you could talk about when there's multivariate random variables. The first one is this like joint probability distribution, which is the probability that any one of these random variables are in some event. So this could be like, let's say this thing represents a coin flip and this thing represents a dice roll. Then you might have the case here, which is like, what is the probability that the coin flip is in the event, which maybe is just heads? So what's the probability that I get heads? And here it's like y is in some event. So this is a dice roll. Maybe the event is like that I get numbers 1, 2, or 3. So I would read this as like the probability that I get heads, and right, this should be read as and. This is like you want both variables taking these values, and the dice roll is the numbers 1, 2, or 3. Okay, so what's the chance that both of these things happen? Right, we're talking about two random variables, so this is like two experiments, and we want to know the probability of something happening in the first experiment and something happening in the second. Okay, this is the joint. Then there's the marginal, which is that you basically don't care about some of the parts that happen, like some of the random variables. So maybe I don't care about what happens to the dice roll, right? So like I do flip a coin, I roll a dice, but I don't really care what happened to the dice. I just care about the coin, and for this, these things are called marginal distributions. So you're just talking about the probability over one of the random variables x, and you just forget about the other one. And once again, all of these things are calculated through their corresponding PMFs and PDFs, which are in the formula sheet. And yeah, so you just use those, but like the situation in which you use one or the other is what I'm trying to like communicate, the intuition of like when would you use one or the other. So marginals is when you just care about like one of the random variables and you kind of disregard the other. It doesn't matter what happens for the other one. Okay, so you can talk about that for x, and this would be the marginal distribution for y. Okay. And then there's a third distribution that you talk about, which is the conditional. And this is the distribution where like you care about one random variable, but you care about it conditioned or like given that you know something else about the other one. So in this case of flipping the coin and rolling the dice, okay, maybe the dice isn't super informative to you, but like you can still say like, okay, if I rolled a 1, what's the probability that I get heads or tails on my coin? Well, in this case, we're going to find out that like, okay, the dice roll doesn't affect anything, so it doesn't really matter if I conditioned on it or not. But in the case in class where like we had arthritis and you're being old or young, then there was some intuition as to why conditioning would affect something, right? So like if I condition, if I know that, let's say, I'm old, right? Then if I talk about the probability of me having arthritis or not will change, probably, conditioned on the fact that I'm old or young. So yeah, so there's notions where conditioning sometimes matters, sometimes it doesn't. But anyways, there's a distribution for this conditional stuff, and you write it as like the probability of x conditioned on y, or the probability of y conditioned on x. And so there's these three distributions. And okay, there's another like useful thing for computing these distributions sometimes, specifically in the joint case, which is that the PMF or the PDF can always be rewritten as these like conditional and marginal PDFs and PMFs in this way. Okay. So this is like useful if you need to rewrite things, or maybe you only know these, but you don't know the joint, then you can calculate instead. So there's this useful property. Then there's this, like when you also have this multivariate random variable, there's this idea of independence. And independence is like, can be interpreted in two ways. Okay, so I wrote only the one way here, but independence is, so you have a multivariate random variable here. Let's say we have n different random variables. The classic example of this is like you have n different coin flips. Okay, so I have one coin, I flip it n times. Each one has some like random, like it either becomes heads or tails. And then I want to talk about what's the probability that like the first coin is some value and the second coin and so on and so on. So what I do, like, okay, I want to talk about this thing. Well, it turns out that if these random variables are independent, then they have this property where you can write the PMF or PDF as just the product of all their individual marginal PMFs and PDFs. Intuitively, like this is mathematically what happens. So like you can always check this if this applies or not to your case. So like if you're given this thing and you're given the corresponding marginals, then you can just check if this property holds or not, and then you know if your random variable is independent or not. But usually what happens is you're told that like, okay, I have these random variables and they're independent. And the important thing like that tells you is that like, if I want to calculate probabilities, I don't need this complicated joint PMF or PDF. What I really do need is just each of these marginals. And you're usually told just the marginals. So you're told like, oh, the probability distribution of each coin is, let's say, a Bernoulli. And you're never told anything about this thing. But that's okay, because since you're told they're independent, then you can just calculate them through this equation. Okay. Yeah. So that's independence. This comes up a lot. Like I tell you things are independent. What that means is that you can do calculations by just multiplying each of the corresponding PMFs or PDFs. Okay, there's a couple questions. Is independence if and only if? Yeah, it is if like, I mean, I don't know, like, if they are independent, then this holds, yes. And if this holds, then they're independent. So it goes both ways. And can you explain what P of X conditioned on Y? I'm not sure where that actually came up. Oh, I think I know what they mean. So yeah, they're asking like, what is this mean and what does this mean? So this is shorthand for the slightly longer thing which we've written before, which is this is the conditional PMF or PDF of Y given X. And usually it's written like this. But I've excluded this because, like, once again, I said, usually it's obvious from the context what you're talking about. So this would be the conditional PMF or PDF. And what is this thing? Well, okay, there's a formula to calculate it and stuff, but the important thing is that this is the thing you will use to calculate the conditional probability, right? So each one of these is a distribution. And the only way we know how to calculate distributions is using PMFs or PDFs, right? And the corresponding PMF or PDF you use depends on which one you're using. So if you have a joint, you want the joint distribution, use the joint PMF or PDF. If you want the marginal distribution, this will be equal to like the sum or the integral, let's say, of little p of x, right? And then for this one, this is exactly where you would use, like, let's say, the sum or the integral of py given x. And so, yeah, that's where this is important for calculating this object. Well, this one, I guess. So, yeah, same story always applies. You use the correct PMF or PDF to calculate your probabilities. Yeah. So like if you only care about this thing, then you don't need this at all. Maybe is the end. Like, so okay, I wrote this because these are like the two marginals you could have. But if you're asked just for the marginal of x, you never need to calculate this. And then maybe you were asking like, why should I care about y at all, like to begin with? Well, it just might happen that like, oh, you have some experiment or something, and you have both of these things, and then you were doing something with it. I don't know, you cared about maybe the joint for some reason, and then later you were like, oh, actually, I also want to ask this question, which is like, what's the probability that I have arthritis? Forgetting about my age or whatever, doesn't matter. What's just like the raw probability of having arthritis? Like, doesn't depend on anything else. So yeah, so these are like questions you might ask about like experiments that you've already kind of done and stuff like that. But if you'd never care about anything else, you can just start with this, and it would just be like the univariate case, and it never cares about anything, and yeah, you wouldn't need this and stuff to begin with. So yeah, it really depends. But then like in that point, you probably wouldn't have even gathered data or had another random variable y at all to begin with. Like if you just cared about some probability, like rolling the dice, you probably would have never introduced random variables about a coin flips and someone's age and stuff like this. And you would never even have these random variables, and you wouldn't need to do all these other complications and stuff. And the other thing is like this marginal thing ends up being useful for like, for instance, calculating the conditional. There's like this thing called Bayes' rule, which is in the formula sheet that helps you then compute this thing. Okay. That's that story for probability. Okay. So there's a bunch of formulas on the formula sheet about calculating these different cases. And all they really are is just always like, if you want the distribution, you use a PMF or PDF. Which one do you use? Well, it depends if it's conditional or marginal or so on. And then there's formulas to calculate those in there as well. Okay. Then there's an important thing that comes up a lot in the course, which is there's functions of random variables. Okay? And all it is just like, you have a function, you plug in a random variable in the function, well, then it's also a random variable. That's what you need to know. Like, so a function of a random variable is a random variable. And an example is, imagine you have x, and it's a random variable. And I'm just telling you, so like it has some distribution. I'm not telling you what it is, but like I'm telling you where this thing's a random variable. Then if you have some function which takes as input, so it has its domain is the same outcome space as x, and it maps to something like y. Well, then I can write things like this function with input random variable x. And this thing is a random variable. So like maybe it's the function x squared. So this is a random variable. That's like all I really want to communicate. And then you can do all sorts of things with it, which is you can talk about its probability and stuff like this and its expected value, which we're going to cover in a second and so on. And the thing that might get confusing is sometimes people will use another symbol like y to represent this function like x squared. But really, you should remember that like underneath all this y thing is a function, and it's a function of x. So it does some operation on x. And this gets much more confusing, right, when you have function of multiple random variables, and then you hide all that information with like a single symbol y. Okay. And like maybe one example is you've seen this with the sample mean. People write like x bar, but really you should remember that x bar, it's like this function of like x1 all the way up to xn, which then is like x1 all the way up to. So this thing doesn't, when you explicitly write, you can clearly see this thing is like a function of a lot of random variables. It's still a random variable, but it's often hidden in this like kind of simplified notation. Yeah. That's right. So what's going to happen is that you'll be, there was a thing in the course where, like I said, you're never going to need to know how to get that distribution. It turns out to be a complicated story to calculate it. So you're either going to be told what that distribution is of y, or it turns out if you care about expectations, which we get into next, you never needed it to begin with. You can just use the distribution of x to compute expectations, and you never needed to talk about it for y. And definitely for this review, I'm not going to get into the details why you just need that, but the story is for expectations, you only ever need the distribution of x, or the PMF of x, and that's it. So yeah, but that is like an important that's a confusion that might happen, is like this thing has its own distribution, and it usually becomes a complicated equation to calculate, but turns out most of the time we don't need it. Okay. So let's move into expectation variance, and maybe I'll take a little bit less questions so I get through everything, and then maybe we can come back. Okay, expectation variance. So let's just do this general case where you have like a multivariate random variable z. So sometimes I'll talk about z, or I can just talk about just x or just y and so on. Okay. So these are all in the formula sheet, but once again, similar to the probability case, there's like all these different versions of expectations that all align with the different probability cases. Okay, so there's like the univariate case, which is just the expectation of one random variable x. And there is an equation for it, which is just like, yeah, so, what was also the intuition of this expected value? Well, the expected value is the value of x that you expect to see if you take the average of x, like imagine, okay, you have some experiment and x represents the outcome of that. If you perform that experiment infinitely many times, and you take the average of that experiment, then that's what the expected value represents. It's not the thing you expect to see the most often. It's just the average value you expect to see. So in a coin flip, if you represent 1 as heads and 0 as tails, if you take the average of many, many coin flips and it's a fair coin, you're going to get 0.5. Okay, that doesn't even represent heads or tails. That's just a number. So yeah, that's what it represents. And this becomes meaningful when we talk about functions and stuff. Okay, so like similar to how you have this univariate case, there's expected values of functions. And the story is like the formula is basically the same. Instead of using x, you just use this thing. But here it becomes maybe more meaningful. Like for the case in our class, we have this like loss function thing, and we can talk about what's like the average, like what do you expect to see in terms of the loss, which is a value, if you were to like predict houses, like infinitely many houses. Like what's the expected loss you're going to suffer in predicting these things? That's where it's useful. Okay. And the story is the same for multivariate. You just like, the expected value of the function, there's a formula for it, but yeah, now it's the expected value of a multivariate function. You just plug that into the equation. Okay, and then there's like 2 more, which is for the conditional, and so there's the conditional one. And the conditional one is like the expected value of this function, given you know some information about x. The story is there, the same, there's a formula, but like here you end up using, okay, if you remember, these things have like, they're either sums or integrals. And then in there, you're integrating over something times a PMF or PDF. And so here you would use, like in the integral, you would use the PMF or PDF of y given x. So the things that change in all these expectations is the corresponding PMF and PDF you use for the calculation. And then there's another thing called a variance, which you can think of as just being the expected value of a function. So this is the expected value, here's a function. I plug in this function. It's this like squared of x minus its expected value. It's just a function. Okay, so that you should understand like what that object is based on this notation. But there's like an intuitive understanding, which is the variance tells you how much does your random variable like kind of, I guess, variate or move, or how far away it is from its expected value. And you can see that like mathematically, it's like this, how far is your random variable x from its expected value? Okay, so like that, so whatever you get for the variance has this like interpretation. The larger the variance, the more the random variable like kind of deviates from its expected value, if you were to like do the experiment. And there's like another useful thing on the formula sheet. There's like you can write it as, okay, there's another useful expression that might be helpful. Okay, that was the quick thing of probability. How about I skip these questions for now, go over the remaining stuff, which is not too much, and then we come back. Okay, so then there's 3 more sections, which is supervised learning, estimation, and optimization. And from those, there's not too much stuff. Well, here's the story. So we had supervised learning, and this was the setting. So you have a data set, and we wrote it like this. And the way we should think about this is as a multivariate random variable. So right, you have a multivariate random variable with n random variables, and those n random variables are themselves multivariate random variables. Okay, sounds complicated, but like it's just a multivariate random variable with n random variables, each one multivariate. And then we're told that, okay, each one of these random variables, each one of these n random variables has the same distribution. Okay? Similar to if you flip n coins, they all have the same distribution. They're the same coin. Here you could think of same distribution, meaning like you gather the data, let's say from the same city, or from like like from the same city, you gathered house prices or something. And then independent, well, independent means what it means by the mathematical definition, but here it just means that like the intuitive understanding would be that you gathering one house price does not affect the other house price. Like you didn't look at it and then choose to gather a different house price. You just randomly like gathered them without looking at any of the other ones. Similar to how you flip a coin and you just like flip n coins, you're not like looking at the outcome of one coin and then choosing to flip different coins afterwards. But mathematically, there's like an expression, this thing here. We talked about this. But okay, so these are the assumptions. We always assume that the features are feature vectors. So that means they're always in RD for some dimension D. And D kind of represents the number of features you have. And then Y is a label or a target. And depending on what Y is, you either have regression or classification. which I cover in a second here too. Okay. That's like the main setting. That's the things you have to work with. You have this data set. And then there's a couple, like, okay, there's a couple objects, and then we have the objective. So the first object we have is a learner, and a learner is just a function which takes as input a data set. Okay, so this is the set of all data sets. Remember, functions, the domain is the set containing objects that they take as input. So this thing takes as input an element of this set, which is a data set. And it outputs a function, which is an element of this set of functions. That's the learner, and that function we call a predictor. So then there's a thing called the predictor, which is just like this function from x to y, from features to labels. It's in this set. Okay. Then to define the objective, we needed to define some measure of like how good this predictor is. The thing we use for the measure of this is called a loss function. It's a function from one label value and another label value to a number. Okay, so that's what this notation means. It's like, this is the Cartesian, so it would be, you have two label values, right? And then you say, how close are those labels? Okay, why do we have two label values? Well, it's because you have the predicted label and you have the true label. And so this loss function will compare the two and output a number telling you how close they are in some sense. Okay. But then we said, okay, like these things are random variables. We don't really know what they're going to be. Like, we don't know which ones we should be better on and so on. So we say, okay, we want to do good on them like on average. We want to do good on the like kind of, we're going to get different houses and different price, and we want to just predict them well like over the average ones we get. And so the way we did this is we say, okay, we don't care about just the loss, we care about the expected value of the loss. Okay. So that's what this symbol denoted. Once again, it's not on the formula sheet, but in the midterm, if I ever need these things, I just like explicitly define them. And so here, why, like, how can I take an expectation of this thing? Well, it's because this thing's a random variable. And why is that the case? It's because it's just a function of, okay, another function and so on, but the things that are being input to the function are two random variables, x and y. These are the random features and the random labels I'm going to receive. Okay. And the final kind of objective was that we wanted to define a learner, which itself was a random variable because the data set is random, such that this expected value is small. So there's like this, like all you really, like, yeah, this doesn't even come up in the midterm, but this is the objective. We get into much more detail in a few weeks later of this complicated kind of object, which the thing to note is like, notice there's an expectation here, which is talking about the data set. And then each, like this inner term L is itself an expectation, which is talking about the X and Ys. So it's a bit of a complicated story, but I just put it here to make things complete. Okay, so then the important things to actually like, that you should definitely know is this idea of regression and classification and the distinction of it. Okay. So all that, like the only difference is in what the labels or these targets, how like what they represent. That's what the difference between regression and classification is. So if the set of labels, right, this is the calligraphic Y is your set of labels. If Y has some notion of order, and usually that just means like Y is some real number or it's some interval, okay, then it's a regression problem. Like for house prices, there's a notion that the price $350 or $350,000 is closer to $400,000 than, let's say, $1 million. So if you have this kind of notion of closeness in terms of your labels, then this is a regression problem. And there we use the square root of the absolute loss. And for classification is just the other case. If there's no notion of order, so your sets are usually these small, like finite sets. And examples are like cat, dog, and bird. And here there's no notion of order. Like I wouldn't say a bird is closer to a dog than it is to a cat or something. Okay? That's really the difference. And you use the 0, 1 loss. Okay. And then we ended this like supervised learning thing with like basically defining the algorithm that's going to, or like, not, I should say the learner function that's going to be used throughout the course. And all we're going to do is just maybe change the estimation or change the optimization stuff. Okay, so what was this like learner thing? It was very simple. It was like your goal was to pick a predictor such that the expected loss was small. But you don't know the expected loss. So what do? You use your data set, right, to estimate the expected loss, and we call that estimate L hat of F. Okay, we want to pick the best predictor, and we want to pick the predictor that minimizes the expected loss. if L hat of F is a good estimate of L of F, right, for all F, then using this and picking the best predictor based on this should be a good idea. And so that's what the optimization step does after, which it says pick the F hat to just be the F, like the best predictor in your function class, such that this estimate of our expected loss is small. Yeah, so the one that minimizes this. Okay. And so like this is obvious, like, okay, just pick the best one over this set of functions. And the only like thing that you need is that this thing is a good estimate of this. So that's the idea of the algorithm. And then we like talked about the two kind of like how we're going to do these two steps. Okay, so those were the last two things. And this, yeah. So there was estimation. And here I just kind of told you what we're going to do for estimation. And I told you that we're going to do it and it's sort of a good idea. I gave some intuition why it's a good idea. And then that's where I left it. So that's all you need to know. And what was that story? That story was like, if you have random variables, I'm sorry, if you have some random variable x, and that random variable has some distribution p, then you might be interested in its expected value. And by might, I mean like you actually, if you're interested in it, then, but you don't know what it is, you can try to estimate it. And the way you would estimate it is you would just gather like n samples of this random variable. So imagine you have a coin, right? It has clearly has some probability of becoming heads or tails, but you have no idea what that, like what the probability is, or like the expected value is of this coin, right? So this expected value actually tells you exactly the probability, it turns out. Okay, so you don't know the expected value of the coin becoming heads or tails. And so you want to know what it is. So what do? You get like n flips of the coin. You represent those n flips of the coin like this. And then you use that to estimate the mean. And what is that estimate? We call that estimate the sample mean estimate. Okay, so it really is just a function of those n coin flips. That function is just like, it's exactly the average. It's the average over the n coin flips. We call this thing the sample mean. It's the mean, right? The expected value from samples. These are the samples. And you'll often see this, like, once again, this symbol x bar being used to represent this function, or mu hat, which means like this hat means like the estimate of mu, which is the true expectation, and you'll see all this notation. Okay, the two important properties to know about this thing is that the sample mean estimate, its expected value, so the expected value of the sample mean estimate, is exactly the expected value of the original thing you tried to estimate. And since all of the random variables are like this IID thing, which means they're independent and, importantly, identically distributed, they all have the same distribution, right? It's the same coin here. Then the expected value of the first coin and the expected value of the second coin, they're all the same. Because if you, like, turns out they're all the same because if you just like write out this formula, they all use the same PMF. They have the same distribution. So yeah, so all these things are the same, and that's a really good result because it tells us that this thing, if you flip these n coins, the average you're going to get from these n coin flips is going to be the true expected value on average. So if you did like these n coin flips many times and you calculate the averages, then the average of those averages is actually this. And then there was this idea of like, okay, like sure I do this experiment of n coin flips, but like sometimes that average will be close to the true average, sometimes it won't. Like I know on average it'll be close, which is what this tells me, but then there's this idea of like how much does it variate from the true average? And so this was the variance. So this tells me the variance of the sample mean. And it turns out that this thing, like we talked about how to calculate this, but this variance was equal to the true variance of the actual coin times 1 over n. So this tells us that if I use more samples, then the variance goes down. Meaning like if I flip n coin flip, like if I have n coin flips and I increase the n, I flip more and more coins, and then I use that as my average, that'll be a better and better estimate. So I'll have less variation from the true expected value of a coin flip. Okay. That's all you really need to know about estimate. That's all that happened. This was like the motivation for why you would use the sample mean estimate is because its expected value is the true expected value, and its variance goes down as you increase the number of samples. Okay. And then we're gonna use like that's what we end up using for the loss. Okay, and then the final thing was this optimization stuff. And yeah, this also should have probably been just review stuff from calculus. but maybe you see some slightly new notation, which is we write this min of the function to represent the minimum value that this function takes over this set. And this is equal to that function evaluated at W star, where W star is the arg min of this function. And here the arg min represents the value of W in the set that achieves the minimum value of this. Okay, so these are all like, these are equivalent. You should know these things. Okay. And then, yeah, there's these properties where like the arg min of the function is equal to the arg max of the negative function. And that the min of the function is equal to the negative of the max of the negative of that function. Okay. Just some properties. The things you really need to know is how to like actually solve the optimization problems. And there's two cases, which is like if the set W, which you're searching over, if it's discrete, then what do? You just like plug it into your function and just compare all the values and pick the smallest one. That's easy. If it's continuous, then you're going to be in some trouble because there's infinitely many points on an interval. Like you can't test your function for infinitely many things. So what you're going to have to do is you're going to have to use derivatives. And if you're lucky, you'll be able to use them. Okay. So what do I mean by if you're lucky? It means if like certain assumptions are satisfied. And this is like the main focus of the course is this continuous optimization case. So if you have a function, then you can use derivatives to help you if that function was convex and twice differentiable. Okay, and here I just like copy and paste exactly what's from the lectures, which is the way you should think about this. Twice differentiable just means you take the derivative twice, and if it exists, that means it's twice differentiable. And convexity just means that the second derivative is greater than 0. Okay, so like you might be asked questions such as like, you have this function, can you check if it's convex? Well, what do? You take its second derivative, and then you check if it's greater than 0. Okay. Then if you found out that it's convex, then you can like find its minimum value by using one of these two cases. And the two cases are also quite straightforward. It's like if the domain is just all of R, then just take the derivative and set it to 0. This is the classic thing you've seen in calculus. But if the domain is some interval, then what you'll have to do is you'll have to do this thing again, set it to 0. But if you find out that the solution to this is not in the interval, then that might be the case that the minimum is not in, like it's not actually this, the value, the solution. And what you should do is you should check your function at A and B, and then compare those two values and pick the minimum of those two. Okay, and then there were some plots showing why this was made sense and so on. So that's what you're gonna have to do to calculate, like, you're gonna, like, yeah. You'll definitely be asked at least one question, which is saying something like, you have some function, find its minimum value, and I'll tell you like, oh, it's convex, and I'll tell you what the domain is, and then you should know, okay, it's a continuous domain, let's say, and so on. And then to finish things off is where we ended was like, you can do the same thing for the multidimensional case. And in that case, you also need for the function to be convex and actually twice differentiable and so on. But the thing I pointed out is that like calculating this is more complicated. And so I will just tell you, if it's in the multidimensional case, that if it's convex and whether you can do this thing, like whether you can do optimization in this thing. Okay, so look for that in the questions. I'll be saying like this function is convex. Find the minimum or something. And the story was, how do we calculate this? Where it was almost the same as the single dimensional case, except for the derivatives. Oh, okay. Also in the multidimensional case, I'll just always, it will never be with intervals. It will just always be in these like RD. So it's always just like this first case. You never need to check the endpoints. It's just always going to be RD. Okay. And this turns out to be like, why am I saying this? Because like in machine learning, this is almost always the case. We always pick our features to be vectors in RD. So this almost always like holds. Okay. And the way we calculate this is now we have a vector solution. So this is the vector that minimizes the function, right? You can just write a vector as this like thing which has d dimensions or d indices. And then what you do is you calculate each one by one. And you do it in exactly the same way as before, which is now you take the partial derivative of the function with respect to wj, and then you set it to 0. And you do this for all wj. So you would do this basically for w1, w2, w3 up to wd. You set them all to 0, and then what do you get? You get w star j for each one. You put it together into this form, and you get the solution. This tells you the point in d dimensions that achieves the minimum of the function, right? So like one more thing I can write, which is that g of w vector star is the, oh, I shouldn't write that. Maybe I write that definition, which is that this thing is equal to the min. The reason I couldn't write it is because here I had the argument, right? So this thing is the min. So this is why you care about it. Because at this value, you actually achieve the minimum value of your function. Why is this all important for machine? Like, you want it to find the, it's going to be a function, but like you want it to find the function that achieves the minimum estimated loss. Well, this is how we're going to do it. We're going to search over these W's, and this thing's going to be like our estimated loss and so on. Okay. So that is the whole review. There's nothing else to say. I can take like 1 or 2 more questions. Yeah, let me take 1 in class and 1 online. That's right. Yeah, the question was whether it was 25 multiple choice questions, and the answer is yes. And someone asked to explain this min GW thing. Yeah, it's just like this. This thing is the value of G of W. That is like, it's the minimum value of this function. And it's the minimum value over all W's in this set. And it turns out W vector star is the W in this set that achieves exactly this minimum. So that's why they're equal. Okay, I will stop recording there.